First question, a toroid of n turns means radius r and cross-sectional radius a carries current I. It is placed on a horizontal table taken as xy plane, its magnetic moment n. Okay, so first of all, a toroid can be considered as a ring-shaped closed solenoid. Hence, it is like an endless cylindrical solenoid. The magnetic field is only confined inside the body of a toroid in the form of concentric magnetic lines of force. For any point inside the empty space surrounded by a toroid and outside the toroid, the magnetic field is zero. Because the net current enclosed in these spaces is zero, thus the magnetic moment of toroid is also zero. In general, if we take r as a large distance outside the toroid, then m is inversely proportional to r cube. But this case is not possible here. So correct answer for this question is option C, that is 0, otherwise there would be field failing as 1 upon r at a large distance, 1 upon r cube at a large distance outside the toroid. Option C. Looking towards the next question, the magnetic field of the earth can be modeled by that of a point dipole placed at the center of the earth. The dipole axis makes an angle of 11.3 degree with the axis of the earth. At Mumbai, the declination is nearly zero. So the magnetic field lines of the earth resemble that of a hypothetical magnetic dipole located at the center of the earth. The axis of the dipole does not coincide with the axis of rotation of the earth, and it is tilted at some angle, like angle of declination. Here in this situation, the angle of declination is approximately 11.3 degree, which is given with respect to the later. Here two possibilities arises, and the declination between them is 11.3 degree west to 11.3 degree east. So correct answer is option A, that declination varies between 0.3 degree west and 0.3 degree east. Option A. Looking towards the next question. In a permanent magnet at room temperature, magnetic moment of each molecule is zero. Individual molecule has a non-zero magnetic moment which are all perfectly aligned, domains are partially aligned, or domains are all perfectly aligned. So at room temperature, permanent magnets behave as a ferromagnetic substances for a long period of time. At room temperature, the permanent magnet retains ferromagnetic property for a long period of time. The individual atoms in a ferromagnetic material possesses a dipole moment, as in a paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a macroscopic volume called domain. Thus, we can say that in a permanent magnet at room temperature, domains are all perfectly aligned. So, the correct answer for this question is option B, that domains are perfectly aligned. Looking toward the next question, consider the two idealized systems: a parallel plate capacitor with large plates and small separation, and a long solenoid of length L greater than R, radius of cross section. Now first E is ideally treated as a constant between plates and zero outside, and in second, magnetic field is constant inside the solenoid and zero outside. These idealized assumptions, however, contradict fundamental law as below. So we are supposed to look for the correct answer. So the electrostatic field lines do not form a continuous closed path. This follows from the conservative nature of electric field, while the magnetic field lines form the closest path. Now, according to the Gauss law, closed integration of E ds is equals to Q upon epsilon naught for electrostatic field. It does not contradict for the electrostatic field, as the electric field lines do not form a continuous closed path. According to the Gauss law in magnetism, closed integration of B ds is equals to 0, which implies that the number of magnetic field lines entering the Gaussian surface is equal to the number of magnetic field lines leaving it. Therefore, case 2 is not possible. So the correct answer is case 2 contradicts Gauss law for magnetic field. So the correct answer is option B. Looking towards the last question, a paramagnetic sample shows a net magnetization of 8 ampere when placed in an external magnetic field of 0.6 Tesla at a temperature of 4 Kelvin. When the same sample is placed in an external magnetic field of 0.2 Tesla at a temperature of 16 Kelvin, then the magnetization will be. So we know that according to Curie law, we can deduce a formula for the relation between magnetic field induction, temperature, and magnetization. It is given as I directly proportional to B upon T. So I can write I2 upon I1 is equals to B2 upon B1 into T1 upon T2. Let's suppose here I1 is equals to 8, this given. Then B1 is 0.6 Tesla, T1 is 4 Kelvin. Then B2 is 0.2 Tesla, T2 is 16 Kelvin, and I2 is what we are supposed to find out. So when we substitute all these values over here, I2 is what we are supposed to find out, the whole upon 8, which is equal to 0.2 upon 0.6 into T1 is 4 and T2 is 16. When we cancel out all these things, we get I2 equals to 2 upon 3 ampere meter. So the correct answer for this question is 2 by 3, that is option B.